Welcome to section 3.9 where we're going to be talking about related rates. So everything that we learned in the previous section on implicit differentiation will come into play here because now we are going to return to our theme of derivatives as rates of change in problems in which the variables change with respect to time. So we want to make sure that when we're talking about some of this implicit differentiation stuff, that when I'm looking for dx over dt, that this variable is now t that I'm taking the derivative with respect to. So anytime I don't have a variable that agrees, then we have to do that extra implicit step and put that derivative notation within there, okay? The essential features of these problems is that two or more variables which are related in a known way are themselves changing in time. For example, an oil rig springs a leak and the oil spreads in a roughly circular patch around the rig. If the radius of the patch increases at a known rate, how fast is the area of the patch changing? So we talk about a radius increasing and about the area changing. So those are the two things or the two variables that we are looking at changing with respect to time. Now, the second example looks at two airliners approach an airport with known speeds. One is flying west, one is flying north. Speeds are rates of change. How fast is the distance between the airlines changing? So there are three variables this time changing with respect to time. It is the position, if I could spell right. The position of the two planes, are two of them, and then the distance between them is the other to make the three, okay? So making sure that you're able to identify those rates of change is important when we are working with these types of problems. So let's just kind of look at a specific situation without any application. Can we take a derivative of this equation implicitly in respect or with respect to time, and then can we figure out the answer? All right, so here we are given xy equals 20. I need to find dx over dt when x equals 2 and dy over dt equals 10. So we're doing this with respect to time. So I must look at this side of my equation and determine how that I have to take a derivative of that. Now, those are two things that are being multiplied together. So I have to engage the product rule in order to do that. So when I do the product rule where I take the first function, which is x, and multiply it by the derivative of y. Now the derivative of y itself is just 1. But if I'm taking it with respect to time, the t and the y do not agree. So therefore I need a dy over dt for this. Then I'm going to add to that the second times the derivative of the first. So the second, the derivative of the first is 1, but it is with respect to time, it would engage one of those implicit pieces of dx over dt. Okay? Now, that has to equal, in my equation, 20. Well, the derivative of 20 is 0. So at this point, we have the calculus that is done. We can choose to use algebra to be able to solve for dx over dt so that I can plug in those values after that. So let's do that. If I'm going to solve for dx over dt, I would need to take this term over here. So I get y dx over dt is equal to, when I bring this over here, I have to subtract it. So it would be a minus x dy over dt. Now, if I want to get this by itself and it's times by that y, then to undo that, I must divide by y and divide by y. Therefore, dx over dt is equal to negative x dy over dt all over y. And so here, this is where, now given this information, can I plug those values in here and find out what dx over dt is? All right, so let's do that. I'm going to plug in values. So I'm going to say dx over dt, let me change the thickness, is equal to the opposite of x, so I'm going to go a negative 2, times dy over dt, which is 10, all over y. But I come up here with what they gave me, and they did not give me y equals. But I am given an advantage of having this equation at the beginning, that if I know x, can I plug that into my equation to find out the y value? Well, absolutely I can. I can put the 2 in for x, then it's times by y has to equal 20, and when I divide 2 both sides, then y equals 10. That's what I want to put in the denominator here for this. And so when I do that, simplifying this fraction, negative 20 over 10, gives you negative 2, or you can think about canceling out the 10s. Negative 2 would be our answer for dx over dt. Okay? All right, very good. So that's just kind of warm-up problem in a sense. We are now going to turn our attention to some application. So in order for you to have some kind of strategy for these application problems, here are some steps that you want to take. Number 1 is to read the problem very carefully. That's in any word problem that you encounter. Making a sketch to organize the given information is really important. Then you want to identify the rates that are given and the rate that is to be determined, as well as any other piece of information that is known. Number 2, we want to write one or more equations that express the basic relationships among variables. I will tell you there are a lot of geometric formulas that you would like to have here. So make sure that you know area, circumference, volume of different kinds of shapes, because that'll help you out. Now, be careful in this step to not quickly plug numbers in. You want things in general, because in step 3, we need to differentiate that problem or that equation in order to kind of get us set with respect to time. And then I can plug some values in, which is number 4, and then solve for the desired quantity. Now, of course, the last one is to check that units are consistent and that the answer is reasonable. So let's turn back to that first example that we talked about with the oil rig, and let's do some problem with that. It says that an oil rig springs a leak in calm seas, and the oil spreads in a circular patch around the rig. If the radius of the patch increases at a rate of 30 meters per hour, there's a rate right there. How fast is the area of the patch increasing when the patch has a radius of 100. So, I guess you could draw a picture. Let this be our oil rig, and then here's a circular piece around that, signifying the oil. So in here we have a certain radius for that, and we need to identify in step 1, what are the things that we are given. So it says that the radius of the oil patch increases at a rate of 30 meters per hour. That is the rate that our radius is changing with respect to time. So in our notation, that's what we're going to call dr over dt. And that is equal to 30. And it's increasing, so we would end up having that be a positive number. Now, it is asking me for how fast is the area increasing. So that is the rate of change that we are looking for. We're going to call that dA over dt. And I want to know what that is when the patch has a radius of 100. So here, r equals 100. So that's all the given information and all the pieces that we need to find. We now need to figure out what is the equation that relates all of those things together. Well, we're talking about area. We're talking about radius of a circle. So let's start with the area of a circle, which is pi r squared. Let's see if we can use that in order to find our rates of change. So when we do that, I need to now differentiate that equation with respect to time. So that means I want to take the derivative of a, which is 1, but with respect to time, that means I have to include that implicit piece of dA over dt. Equals, I'm going to take this 2 and this power out front in front of just a constant. Remember, that's just a number. That's not a variable. So I'm going to take this 2 out front, reduce that power by 1, which gives me a 1. I'm not going to write it. But you just took a derivative of the variable r, which does not match the rate of change in the bottom, which is a t. So that means I have to engage that implicit derivative as well. Okay? So at this point, this is when I've differentiated. Now it's time for step 4 for me to plug values in. Again, do not plug values back here because things are changing. Now we want at a specific time, what is dA over dt when my radius is 100, so I'm going to plug in 100, and the rate of change of that radius for my dr over dt is 30, and now I'm going to run those numbers together. Now we're going to keep it in terms of pi, so I'm going to do 2 times 100 is 200 times 30 is going to be 6,000 pi. Now, obviously, you can get a decimal for that, but you don't have to. You could leave it all in terms of pi, so this 6,000 pi. Now, we have to do our units here, and I don't worry about putting my units in here. I worry about, okay, right here, what's the unit measure of area? Well, in terms of meters, area would be meters squared over time, and our time unit in this problem is hours. So we would have meters squared per hour being our final answer there for this problem. Okay? All right, very good. Let's move on to our next one, which kind of goes along with the second example that I gave you above on that side. Here, though, I give you kind of a little note. You may need to brush up on some of your area and volume geometric formulas for these types of problems, so make sure that you do that and know what they are. Here we have 2 small planes that approach an airport, one flying due west at 120 miles per hour, aka our rate, and the other flying due north at 150 miles per hour, another unit of rates of change. Assuming that they fly at the same constant elevation, that means they're at the same height. That doesn't put in another dimension to our problem to make it a little bit more difficult, which is good. How fast is the distance between the planes changing when the westbound plane is 180 miles from the airport and the northbound plane is 225 miles from the airport? All right, very good. So we need a picture. I'm going to let my airport be here. Now, I've got 2 planes, one that's flying west into the airport and another that is flying north into the airport. So here I have a plane coming in here. We're going to call this our westbound plane. And then I have a northbound plane that's coming in this direction. Call it in. And I have a distance between those. So north and west are perpendicular to each other. Hence we have a nice right triangle here. Maybe you might know something about a right triangle when you're dealing with the sides of a right triangle. Now, this is an x direction, so I'm going to let that be x because, again, that distance is changing, so you don't want to put a number there just yet. At the instance we're wanting, you want to be generic at first. So I'm going to let that distance be y since that's going in the up and down direction for the y-axis. And I'm going to let this one be z just for kicks, okay? X, y, z here. Z is that distance between those 2 planes. So, we've drawn our picture. Let's see what we are given. It says that our westbound plane is flying at a rate of 120 miles per hour. So this is our variable x. Therefore, the rate of change with respect to time is dx over dt. That is 120, and notice we are in miles per hour. Now, I'm going to put a negative on that because it's going in the negative direction. Actually, it's a decreasing rate where you are getting closer and closer and closer. The value of that is decreasing, okay? The distance here is decreasing. Also, this distance here is decreasing as well. So then for our rate of change in the y direction, dy over dt is also going to equal a negative 150. How fast is the distance between the planes? Here is the distance between the planes. That's what I'm looking for. I'm looking for dz over dt. That's what's in question when the westbound plane is 180 miles. So specifically when x equals 180. And when the northbound plane is 225 miles. So when this distance is 225, therefore our y is 225, okay? So that is all step 1, drawing your picture and figuring out what you are known and what is unknown. Now, step 2 says that we must find that equation that relates our variables. So here we have a right triangle. there's a theorem in mathematics that you must know when dealing with right triangles. If you are given the three sides of a right triangle, they are related by the Pythagorean theorem. Therefore, a leg squared plus a leg squared equals a hypotenuse squared. So I'm going to write x squared plus y squared has to equal z squared, and that is the formula I'm going to use for this specific problem. Now remember, do not throw numbers in. This is a specific instance in which I'm looking for an answer, but I cannot plug that in until I have differentiated this formula. So I'm going to implicitly differentiate this with respect to t. There are no t's, so every time that I take a derivative of those variables, I need one of those rates of change, dx over dt, dy over dt, and dz over dt. So take the derivative of x squared, bring the 2 out front, decrease that by 1, gives me 2x. But then I have to do my dx over dt. Likewise with the y, I get 2y times dy over dt. And likewise, just like the others before, 2z times dz over dt. Now, after you've done that calculus, it's time to throw in those numbers, okay? So here's all the numbers that I have, and I need to throw those things in. Now, actually, before I do so, notice that each one of those has a 2. If I want to make life a little bit easier on myself, I can get rid of those 2's. So I have a 2 with every single factor, so if I do that, I get rid of the 2's and be left with x times dx over dt plus y times dy over dt equals z times dz over dt. So, here's the deal. I'm out to find dz over dt, which is over here by itself. So in order to get that by itself, I must divide by z, which means I have to divide all of this by z as well. Or you could do the individual terms by z if you want. Okay, either way works. Now, if that's my dz over dt, that means I got to plug in numbers to all of that. Okay, now you can rewrite that, but I'm not going to. Just kind of get rid of that. There's your dz over dt, okay? Now, I have an x, which is 180. I have dx over dt, which is 120. We have y. We have dy over dt. But notice, I do not have z. But I do have x and y, and I have a formula here that relates each one of those. So, that means I have to do 180 squared plus 225 squared has to equal z squared. And when you add those two squares together and take the square root to get z, I will tell you that z is equal to 83,025. Now, can you get a decimal to that? Absolutely. Throw it into your calculator, but I don't want decimals until the very end, okay? All right, so now we have all that we need. Let's throw in x, so we get 180 times dx over dt, which is negative 120. Add to that the y value, which is 225. Oops. Undo that. Times the dy over dt, which is negative 150. All over the z value that we found, which is the square root of 83,025. And that right there is my dz over dt. Now, you can throw that into a calculator if you so choose. And you will end up, if you then divide by that square root, you end up with negative 192.1 as our dz over dt. Now, that's a rate of change of a distance over time. What is our distance in this problem? It is miles. The time is hours. So this is miles over hours. So a miles per hour. And that would be our rate of change that we need for that problem. Okay? So the distance between those two planes is decreasing, and the distance is getting smaller at 192.1 meters per second. And that's what that means right there with that minus and that number. Okay? All right, very good. Let's try this one. A child is flying a kite at a height of 40 feet. That is, moving horizontally at a rate of 2 feet per second. If the string is taut, at what rate is the string being paid out when the length of the string released is 50 feet? All right, so we have a little child flying a kite. However you want to draw your kite, okay? We have a height that is 40 always. Now, is that changing or is that not changing? And I'm hoping you're screaming at me telling me that it's not changing, because if it's not changing, that means that I can go ahead and put that in my problem. Okay, you do not have to have something that is constant be put in later. You can put it in at the beginning. All right, we have a certain distance here to our child, and we have our kite string that is right here, okay? Now, we have a certain distance that is moving. It is changing. It's going horizontally at 2 feet per second. So that distance, we're moving horizontally 2 feet per second. That means that dx over dt is equal to 2 feet per second. Okay? Now, we also have this distance here, which is our string. And it says, if the string is taut, at what rate is the string being paid out? What does that mean? I'm looking for this rate of change for dz over dt. That's what's in question. What is that rate when the length of the string released is 50 feet? Here's the length of my string. So basically they're identifying here that z equals 50. Okay? So, step 1, draw a picture and do all of your givens and what your unknowns are. So make sure you do all of that, okay? Step 2 is to write the equation for our relationship here. This is another right triangle. So hopefully the Pythagorean theorem is one that is in your mind right now. So we are going to then go x squared plus 40 squared equals z squared. Now again, I can put the 40 in because it's never changing. If something is changing, you better keep it as a letter. So there's my relationship. I now need to differentiate that with respect to time. So I'm going to take the derivative of this as 2x times dx over dt. Set that equal to, because what's the derivative of 40 squared? It is just a number, therefore the derivative is 0. Take the derivative of the right side, gives me 2z times dz over dt with respect to time. And so now, what are we looking for? We're looking for dz over dt. So I need to get this by itself. I'm going to divide by 2z and divide by 2z. Now that's kind of nice because these go away. Also, those 2's go away. So I'm going to rewrite what dz over dt is equal to. It's equal to x times dx over dt all over the z value. And now, do I have all of those values to plug in? Well, I'm looking at x to start with, and I don't have an x equal. So what does that mean? That means I have to take z equaling 50 at the instant that I'm asking the question, along with the other sides, to determine what x is. So by the Pythagorean theorem, x squared plus 40 squared equals 50 squared. You can also plug it right up in here. Either way works. Then when I subtract 50 squared minus 40 squared, well, that's 2,500 minus 1,600. Gives me 900, and when I square root both sides, therefore x equals a 30. So that's what, that is what I want to put in right there. So dz over dt, let's plug our numbers in, is equal to 30 times dx over dt. Now dx over dt means that we're going moving at a rate here of 2 feet, so it's a positive. So we're going to go 2 all over z, which is 50. Multiply 30 times 2 is 60 over 50, and I can reduce by 10 to give me 6/5. And our unit, distance over time. Distance over time. So this is in feet per second. That would be a valid answer, but if you want to change it to a decimal form, 1.2 feet per second would be that answer. And those, either two, should be accepted. It would be accepted by me both ways, and hopefully by my lab math, unless they ask you for the decimal or they ask you for the fraction. So make sure you watch what they're doing there, okay, when they ask you those questions. All right, very good. Hopefully you're still with me. Again, make sure you follow those steps in the very first part of these notes in section 3.9. They will help you determine how to get to the answer. All right, so our last problem here talks about coffee is draining out a conical filter at a rate of 2.25 inches cubed per minute. Inches cubed is a volume unit, okay? So you want to make sure you note that. If the cone is 5 inches tall and has a radius of 2 inches, How fast is the coffee level dropping when the coffee is 1/4 feet deep? So we want to make sure that, number one, I didn't emphasize this a lot, but notice here, this is in feet and everything else is in inches. So you want to make sure that you have matching units. So we're going to take that into account when we do our variables. All right, so here's our conical shape filter. Okay, that has a radius of 2 and a height of 5. Okay, it's filled to a certain level with coffee. Okay, all right, now I want you to make sure you see this with the level of coffee. I don't know exactly where it is, okay? But I do know that if I just symbolize it here, that at this point there's a certain radius, and at this point I have a certain height as well. Now hopefully you recognize that as a right triangle. Okay, I have a small right triangle with a radius and a height, and I have a larger right triangle with a radius and a height that is specific to the whole cone. Now, that is important because we're going to need to use that information here with similar triangles in order to help us with this problem. Okay, so that's kind of given to us. We're also given a volume rate of change with that inches cubed. So dV over dt. I always like to look at my units. Now, it is draining out at 2.25. Now, it is going down. It's decreasing. So, it's 2.25. It's getting smaller if you want to think of it that way. Inches cubed per minute. Now, I'm also going to think of this as a fraction. You can keep it in terms of decimals, but I like to work with the fractions. So, this, let me remind you, is 2 1/4. Then you can do your mixed number into an improper fraction of -9/4. Okay. Now, what are we looking for? How fast is the coffee level dropping? Here's where my coffee level is. So I'm looking at what is dH over dt. That's what's in question when we are at 1/4 feet deep. So when h equals 1/4 feet, which is how many inches? Well, if we times that by 12, we get a 3. And that's how many inches it is, okay? So again, make sure that your units match. All right, so the difficult part about this is the volume of a cone. The volume of a cone with a certain radius and a certain height, if you need to look this one up, this is one you don't probably use very often, but it is 1/3 pi r squared h. The problem with that formula is I have V, R, and H. Over here in my given, I'm only given in terms of V and in terms of H. So somehow I'm going to have to get that R out because, number one, when I differentiate, I'm going to have to use the product rule with that, which could get pretty nasty. But I don't know anything about the radius, okay? I don't know anything about the radius's rates of change, nothing. Now, actually, I do know something about the radius, which is right back here. With our similar triangles, if you go back to geometry, that means that our sides are proportional in these triangles. So I can write a proportion relating this radius to that height being equal to this radius over that height. So I could say 2/5 is equal to R over H. And if I want to remove R out of this formula, I need to solve this for R in terms of H. Again, let me say that again. If I need to remove R out of this formula, I need to figure out how they are related so I can get this in terms of H. So if I want to get R by itself, all I merely have to do is multiply by H. Therefore, I can write that as 2/5 H. And that right there is what I want to put right in here. Okay, and this is the tricky part of this problem. The differentiation, whenever we get there, is not going to be bad, but it is the tricky part here. Okay, so let's sub in that 2/5 H. So I get 1/3 pi times 2/5 H that I have to square. Don't forget about this H back here. Then I'm going to simplify this, use some algebra. So I'm going to say, okay, volume is 1/3 pi. Now if I square each of these pieces, I get 4/25 H squared times the H on the outside. And going one more step, by multiplying all my numbers together, putting my H's together, I get a volume. 4 times 1 is 4 pi over 25 times 3 is 75 h cubed. And that is the formula that I want to use in order to differentiate. Again, you know nothing about r in the given information, so you've got to get rid of that r somehow. All right, so let's scroll down a little bit. Let's, at this point, this is the formula that we want to differentiate. So I'm going to take the derivative of v with respect to time. Well, the derivative of v is just 1, but I need my dv over dt because the letters don't match. Then I'm going to keep my constant out front and differentiate my h cubed. So I'm going to bring the 3 out front and decrease my power by 1. But it is with respect to time, so I need to add on my dh over dt. So when I do this, I can kind of change things around by, I can go ahead and plug in h if I want, which is 3, okay? But I could also cancel, I'm going to cancel this into here, give me a 25. So I get dv over dt is equal to 4 pi over 25 times h squared times dh over dt. And now's the time I want to plug things in, okay? Now, you could go forth and solve for dh over dt if you wanted to do so. I'm going to just plug my numbers in at first and then solve it with numbers. So you can do it either way. I'm going to go ahead and use the fraction to make this negative 9/4 for my dv over dt equals 4 pi over 25 times 3 squared, which is 9, times dh over dt, because that's what I'm looking for. Now, what is this? This is actually 9 times 4 gives me a 36 pi over 25. So if I want to get rid of that fraction, that means I could multiply by the reciprocal of 25 over 36 pi on both sides to get rid of this and get rid of that and that. Okay, leaving me with dh over dt on the right side. But remember, if I multiply 25 over 36 on that side, I must multiply by 25 over 36 on this side. And so what does that do? Oh, I forgot my pi, so we need a pi. 9 will go into 36 4 times, leaves me with a 1 on top, so this becomes a negative 25 over 4 times 4 is 16 times pi. So I get negative 25 over 16 pi. That is my dh over dt. So in exact form, that would be my final answer. But as a decimal, when you do this into your calculator, please make sure you get negative 0.497. That is the rate of change of the height in this cone for this particular problem. Now, what's our units? We have height over time. So a unit of measure over a time unit. So therefore, this is going to be inches over minutes. So inches per minute is what we're looking at, and that is our final answer. Okay, so that one is pretty difficult once you have to change from the original volume formula into what you have to get down to differentiate according to what's given to you. So you want to make sure that you practice that so that you're able to do that on a test and such. Okay? So this is all of Chapter 3. We're going to actually move into some more applications of derivatives into Chapter 4, but it's more into graphing, talking about max and mins and critical numbers and points of inflection and such. And so we will kind of be done with these types of applications at this point, and then move into some graphing concepts. So until next time.